Today, on how it's made. Rolled wafers. Wood pellets. And class and championship rings. At some point many centuries ago, the thin communion-style wafer took a delicious twist with the creation of the rolled wafer cookie. The exact origin of this tubular treat isn't known, but it has been traced back to Syrian Christian pastry makers during the Middle Ages. Long and elegant, the rolled wafer is one classy cookie. It's crispy on the outside and creamy at the core for a sweet fusion of flavor and texture. It can be served as a garnish for the main dessert or on its own. It is, of course, a matter of taste. Ingredients for the rolled wafer include flour, sugar, cocoa powder, whey powder, milk powder, and dark chocolate. There are 20 ingredients in total. They load each one into a separate bin. The bins all funnel into one of two big mixers one floor below. One mixer blends the wafer batter, and the other prepares the creme filling. A central computer controls the flow from the bins to the mixers. It measures and releases the ingredients to follow the recipe exactly. The computer also assigns a lot number to each batch, so if there's a problem with the product, they'll be able to track the source and fix it. Down below in the wafer mixer, the batter is looking pretty smooth. They're aiming for a consistency that's similar to pancake batter. A worker scoops some up to check it. Too runny or too thick, and the wafer won't have the right crunch. The batch is just right. The wafer batter now flows onto 4 metal plates that spread it onto an immense rotating wheel, creating 4 very thin ribbons of batter. Gas flames heat the wheel to 150 degrees Celsius to toast the batter strips. At this high temperature, the toasted pastry has yet to crisp up. It's soft and flexible, which means it's ready to roll. Coming off the wheel, the wafer pastry winds around a revolving mandrel and quickly cools, generating a continuous wafer roll. The chocolate hazelnut creme filling is looking delicious by now, and machinery pumps it through a hole in the wafer-forming mandrel. As the wafer takes shape, the mandrel pumps the creme into it. This mechanized system is faster than hand rolling, and the wafers it generates are more uniform. The long rolled wafer now spins off the mandrel and heads into a tunnel. Inside, a little axe swings down to chop it into wafer-sized pieces. The rolled wafers exit onto a slide and make a gentle landing onto a conveyor. The creme inside the cookie is still fluid, and the pastry itself is still somewhat pliable. The next stage of production will solidify everything. It's a trip through a cooling tunnel. On this stage of the journey, the various components of the rolled wafer crystallize to their final form, and they emerge crispy enough to be handled by the employees. They identify any damaged wafers and discard them as they arrange the cookies for packaging. This means compartmentalizing them in groups on a slotted conveyor. After that, the little stacks of rolled wafers travel through a curtain of plastic. Machinery cuts and heat seals the wrapping in this completely automated packaging system. The plastic will keep the wafers fresh, but it won't protect them from breakage. That's the job of the metal can. After an inkjet-like device prints the freshness code on the bottom, the cans ride a magnetized wheel, which flips them to an upright position. A worker then fills each can with the plastic-encased wafers and puts a lid on the job. Modern manufacturing has revolutionized the making of these rolled wafers. Once individually rolled and baked by hand, machinery now does most of the work, producing more than 100,000 rolled wafers per hour. But of course, the taste is still all about tradition. Unlike a conventional wood stove which burns firewood, a pellet stove uses wood pellets as fuel. Made from lumber byproducts such as sawdust and wood chips, which would otherwise end up as waste, pellets burn more efficiently and more cleanly than wood and produce very little air pollution. A pellet stove has an onboard storage container called a hopper, which holds, depending on the model, up to 36 kilograms of wood pellets. Several computer chips monitor the stove's heating performance, dictating the rate at which the hopper automatically feeds pellets into the stove's fire pot. The heat output is manually adjustable or can be controlled by a thermostat. Wood pellets burn far more cleanly than logs, and the fire is smoke-free. Wood pellets are made from a variety of raw materials: sawdust, wood chips, wood shavings, small logs, even scraps of wood left over from furniture and other manufacturing. These different types of lumber byproducts first have to be reduced to the same size and consistency. Therefore, the first stop is a huge grinding machine. Inside, mammoth steel hammers pulverize the raw material to uniform pieces. The raw material contains about 45% moisture, so it goes into a dryer to reduce the moisture level to between 11 and 12%. What was rough raw material has now been ground to a finer state and dried. But it's still not fine enough. So it goes into a mill, which processes it further until it's roughly the size of rice grains. A feed pipe transfers what is now wood fiber to a row of presses. These are the machines which make the pellets. The moisture content of the fiber is critical. If it's too wet, the pellet presses risk clogging up. That's why each pellet press has a readout displaying the fiber moisture level. As an added measure, the factory draws fiber samples and sends them to the quality control lab for analysis. It's essential for the stability of the pellets that the moisture be at the ideal level. Excess moisture would eventually evaporate, breaking the pellets apart. So, to analyze the moisture content, the lab technicians weigh a sample, heat it to a high temperature to evaporate the moisture, then re-weigh. The analyzer is programmed to translate the weight loss into a reading of moisture content. The pellet press is a large drum with perforated rollers inside. The holes are pellet width, a ½ centimeter in diameter. As the drum rotates, the rollers apply pressure. This compresses the fiber by 400% and extrudes it outward through the holes. A knife slices the extruding fiber at programmed intervals, cutting it into lengths of just more than 3 centimeters. The compression generates heat, which draws out the tree sap still contained in the wood fiber. This sap, called lignin, acts as an adhesive, locking in the pellet shape. The journey from raw material to pellet is now complete. The pellets, however, are still quite warm and sticky, so they clump together. The solution? About 15 minutes in a cooler. As the room temperature air blows through the pellets, cooling and drying the tacky lignin, the pellets separate from each other. Some of the processed raw material ends up in too fine a state to become pellets. So, as the pellets exit the cooler, a vibrating screen filters out this sawdust-like material, which incidentally doesn't go to waste. The factory uses it to fuel the dryer. The pellets, meanwhile, proceed to packaging. It's a continuous system. The machine feeds printed plastic film around a cylindrical tube, forming the shape of the bag. Then it drops in 18 kilograms of pellets and seals the top of the bag, simultaneously forming the bottom of the next one. Wood pellet stoves are fast becoming a popular means of home heating. And because pellets cost significantly less than most other types of fuel, wood pellet systems are an emerging option for commercial and industrial heating. A ring celebrating a special achievement makes a cherished lifelong keepsake. Whether it's a class ring to commemorate graduation from high school or a championship ring for the players on a winning sports team, as the years go by, this special piece of jewelry keeps the memories close at hand. Championship rings are entirely custom-made. They typically feature the team name and logo along with the year of the big win. They can also have personalized touches, such as the player's name or jersey number. Class rings, on the other hand, come in several ready-made designs presented in a catalog. Graduates order their favorite style, then personalize their ring by choosing options such as symbols, gemstones, and engraved lettering. For each style, a jewelry designer first sketches the ring's base, the overall shape of the ring, minus the decorative elements. Then, an industrial designer transforms the sketch into a three-dimensional computer drawing. The ring's decorative components go through the same process. The jewelry designer's colored drawing, adapted to 3D software, which guides a computer-operated milling machine. The machine transforms 2 blocks of aluminum into a 2-part mold for each of the flat, detailed components of the ring, meaning all the parts except for the base. A steady flow of lubricant washes away the shards of metal the machine cuts away. Bit by bit, the mold assumes every intricate detail of the ring design. Once it's finished, they coat the cavity with a powder that prevents the wax they're about to inject from sticking. Then they load the mold into an injection device. It shoots in hot liquid wax at high pressure, filling all the minute nooks and crannies of the intricately detailed cavity. Seconds later, they extract a wax model of, in this case, the elaborate top of a championship ring. To make a wax model of the ring's base, they use a flexible rubber mold, because it would be too difficult to extract the 3-dimensional shape from a metal mold. They inject the wax at low pressure, as a rubber mold can't withstand high-pressure injection, nor is it necessary when the base has no intricate details. The next step is to assemble the wax models of 2 of the ring's components, connecting the parts with joining wax, applied using a fine-tipped soldering iron. It's at this stage that they also size the ring for the customer, either cutting out a section of the shank to downsize or adding to the shank to enlarge. Next, they begin building a wax structure on which to mount the wax models for several rings they'll be casting simultaneously. They solder a small stem to each model. Then connect each stem to a large wax rod. When they're done, they have a tree-like structure holding all the wax models. They solder this structure to a rubber base. Then slip a metal flask over it. Next, they mix up some plaster, blending it for a good half hour, under a vacuum to remove all the air bubbles. Then they inject the plaster into the flask, engulfing the wax models and supporting structure inside. Over the next 12 hours, the plaster hardens into a shell around the wax. Next, 12 hours in a hot oven. This burns out the wax components, leaving behind a cavity in the shell shaped precisely like them. Now it's just a matter of melting down the metal for the final casting. The technique of using a wax model to create a mold is known as the lost wax process. This company uses the plaster shell as a mold to cast rings in 3 types of metal: gold, sterling silver, and stainless steel. Regardless of the metal, the ring-making process is the same. In just minutes, the induction furnace has heated the metal, in this case gold, to the required molten state. They carefully pour it into the plaster shell. Gold flows down channels and into cavities left when the wax burnt out. Once the gold cools and solidifies, they submerge the shell in cool water. This instantly dissolves the hot plaster, releasing the cast piece. Everything that was once modeled in wax is now replicated in gold. They cut the ring components off the structure, then remelt the structure to reuse the gold. There's still a remnant of the structure on each ring component, so they grind it off. Next, using a grinding tool so small that it fits through the ring, they smooth the inside surface. Then they stamp in the company name, along with the internationally recognized code identifying the metal, such as 10K for 10-karat gold. To smooth the ring's outer surface, they use a grinding wheel which has splits in its abrasive discs. The splits produce a see-through view as the discs spin at high speed. With the entire surface now smooth, the ring is ready for polishing. They apply some polishing compound, then, using another split wheel, shine it up. Next, the top of the ring goes to the stone setting department, where, using a fine rotary tool, a specialist contours each setting to fit the gemstone's pointed base. Then he sets each gemstone, forcing down the 4 surrounding prongs onto the edge of the stone. Next, he sets tiny diamonds. He presses each one into place, then pushes the surrounding metal inward to hold the stone down. The top of the ring complete, they now solder it to the base. Using an airbrush, they apply a fine mist of black paint, then wipe it off. This leaves behind a black background highlighting the ring's details. They apply some polishing compound to a cloth buffing wheel and polish the ring to a high gloss shine. They clean the ring thoroughly in repeated ultrasonic baths. Ultrasound waves traveling through the water dislodge all traces of polishing compound and other residues. A few blasts of pressurized steam, and the ring is completely dry. Certain rings also have enamel decoration. Enamel is liquid glass. It goes on like paint, then has to be baked in an oven for 30 minutes. Finally, a computer-guided engraving machine inscribes any name or personal message customers request be written on or inside their rings. The tradition of the class ring dates back to the 1800s. Championship rings, a wearable trophy of sorts, are a more recent custom. Both make a proud and triumphant fashion statement.